started for the day. How are we doing? So let's see, your homework was due yesterday night, is that right? Excellent. That's why there's half the people down in the room from Tuesday, I take it. But hopefully you guys will all be back for the nano quiz next week. As a reminder, there's a nano quiz. So like from here on out, there will be roughly a nano quiz every other class. Just to keep you on your toes, I think at some point during the semester it switches from every Tuesday to every Thursday, thanks to like Thanksgiving, or like at some point there's a class that can skip. So if you ever have a question, everything is determined on the course calendar, which went out on you. Also, from here on out, you will have 2 weeks for your homework assignments. The first one is accepted just because otherwise the whole semester kind of gets off kilter. So I appreciate your patience. And I know that students might bellyache about the first one not having as much time, but then I also never see students starting homework more than a couple days ahead of time. So I have mixed feelings about that. But I digress. In any event, any questions about what we're up to procedurally, what's up next? Everything that you need to know for this class is already online, right? Your assignments are on there, your final project instructions are there, the exam dates. So we kind of try to run this thing.
Is this choice C or C1?
Excellent. Okay. Right. So today we'll continue in our discussion of transformations and modeling. So remember in our last lecture, essentially we did a really careful, or at least my version of careful, treatment of different linear transformations, and then how to extend from linear to affine, right? And the kind of high-level point there is that by simply adding an additional coordinate to our points, we can accomplish a lot and extend from just stretching and rotation to also include translation, which of course is pretty critical for a graphic system. Today, kind of similar to how we talked about curves, right? We first constructed a single Bezier arc and then we started gluing them together. Now we're going to do something similar with transformations, right? We talked about a single transformation in our last lecture. And today we're going to chain those things together. And of course, our main motivation for doing so is illustrated on the screen here, which is that we really like to model, what's this guy's name? Bumblebee, thank you. And in fact, if you watch any scene in any film, I thought for fun, we could watch just a moment, we can really appreciate how complicated the composition of your objects is. And the reality the reality of modeling a scene like this is that it takes a team of hundreds of artists, modelers, people who are doing physical simulation and so on to compose all the different parts of this together. It's not like, I'm going to be honest, I don't know, Mark Wahlberg, is that who that is? Like is flying through the air here is somehow actually acting the scene out, right? There's somebody that's doing the physics, somebody that's probably controlling the reflectance off of these different objects, somebody that's doing some character animation because we probably don't want to actually subject our actor to whatever crazy elastic motion there is going on in this scene and so on, right? And so essentially what happens when you put together a clip like this is that, if nothing else, everybody has to agree on a coordinate system. Yeah? This is a goofy way to start this lecture, but it's absolutely true. And in fact, if you think about the coordinate systems involved in the scene, they roughly reflect the structure of the team that probably modeled that video clip, right? They're people that are working the coordinate system of the car, and within that, the coordinate system of the wheels, and so on. There are people that are working in the coordinate system of Mark Wahlberg's belly. And all of these things then have to get assembled together into one final composite scene. Yeah? And so, of course, forcing everybody to like choose the origin to be like, I don't know, Bumblebee's knee or something probably isn't a very realistic thing to do. Yep? Okay. And so, at the end of the day, although sadly what you guys will be rendering won't be quite as detailed as what you see in a film that's rendered by thousands of people working together, the same basic themes still apply here, right? Which is that triangles, parametric curves, surfaces, and so on are the building blocks for complex objects. But hierarchical modeling is all about taking those simple things and combining them together, right? And so the basic philosophy that we'll kind of pursue today is that maybe his hand is attached to his arm, it's attached to his body, and maybe there are even repeating parts, which is going to make things be not quite a tree structure, which is going to make our life a little bit harder. Okay, so that's our basic setup here. So we'll spend like maybe about 20 seconds doing a quick recap of vectors, points, and coordinates. I think I did that to death in our previous lecture, and talking about coordinate system transformations. And then our big goal for today is to chain things together. And in the process of doing that, we'll talk about two problems in kinematics, forward and inverse kinematics. This will also be our introduction to computer animation, which I think is the next big topic in this course. Okay, and kinematics is one of these great topics that you may see in a computer graphics course. You may also see in robotics, where it's extremely important for exactly the same reasons, right? Which is that, you know, when a robot controls its wrist, implicitly the position of your hand is also controlled by all of the joints that are above your hand, which makes your life pretty difficult, right? Like if I want to put my hand here, I mean, if you think about the control problem that's involved, it's quite complicated, the coordination that has to happen there. Yeah? And these are still a lot of open problems, by the way, and I think you see that in video games, you know, like when there are video characters that are kind of directed to do a particular action, like touch an object, you see all kinds of crazy things like their elbows are snapping around and so on, and that's because these are tough inverse problems that people still work very hard to solve. Okay. Right, so let's do a quick recap. So in case you somehow managed to miss it in our last lecture, our basic point is illustrated on this slide, right? We talked about vectors, which are sort of thought of as displacements, velocities, and so on. They admit a lot of different operations, including addition and scaling and so on. And of course, vectors are not the same as points, right? Points are locations in space, vectors are displacements. Right, and I guess something that we maybe didn't cover last time, but you've probably seen before, is to project one vector onto another, you use the dot product. Okay? We'll review that formula when we need it. And the other thing that we talked about quite a bit are coordinate systems. And in this class, for the most part, our coordinate systems are going to be orthogonal, meaning like kind of like the picture that we tend to draw in real life, x, y, and z are perpendicular to each other. Every once in a while, we might shear an object, but then we have to be really careful what it means for an object to be perpendicular. Yeah? And in particular, that's going to pop up with, like, let's say I have a 3D model of a sphere, and I want to model an ellipse. Right? The easiest way to do that might be to take the sphere and just apply a transformation to it. But then a weird thing is going to happen to the normal vectors to the sphere, which are needed for rendering. And at the very end of today's lecture, in kind of a weird appendix, we'll go back and prove that formula if we have time. If we don't, at the beginning of the next one. Okay, so let's talk about coordinate systems just a bit, do a little bit of a fun review here, and also establish today's notational convention. In this class, again, I will never ever hold you guys to notational convention on your exam. If you ever are unclear, like, does this thing go from this to this, or from the other guy to the first one, just ask me, because in reality, like in code, that's not something you would memorize. It would be something you have in a table sitting in front of you. But in any event, just for purposes of having a lecture today, we're going to choose a particular notation. And I triple-checked the slides before lecture, and I think they're consistent. Somebody at the end of our last lecture already caught that one of the slides was incorrect. This is like my least favorite thing to do, so there's high probability of mistake if you catch one, let me know. But in any event, the basic notation that we're going to use is that M12 goes from coordinate system 2 to coordinate system 1. This is convention. Okay, there's nothing mathematical about it. And the reason that this is kind of easier to read is notice that the 2's are right next to each other. Yeah? And so if you kind of read this right to left, you can just look at the leftmost number and that tells you the spacing here. So I think it's a reasonable convention. Does everybody agree, understand what's going on? Okay. Cool. And actually, there's a little formula at the bottom of the slide that I thought was worth spending 10 seconds on. Just because I always get this stuff wrong, and so I want to share with you guys how I can go back in my head and fix it when I get it wrong. So if you're in an exam question, you're freaking out about what direction your matrices go, there's one simple way to remember it. As follows. So let's say that I have a matrix. I'm going to choose a neutral set of letters so that I don't cloud it with the notation of this slide. So let's say that I have a matrix C. Right? And I'm trying to kind of reason my way through what C does geometrically. Yeah? One way that I think is easy to think about, and we'll do an example, is to look at the action of C on the two coordinate vectors, right? Like 1, 0, and 0, 1. So for instance, let's say that I multiply my matrix by 1, 0. What am I going to get? So remember the matrix multiply goes like that. I'm going to do this Macarena a lot in this class. So we're going to add 1 times C11 plus 0 times C12. And similarly here, we're going to get 2, 1 plus not 0 times 2, 2. So what did I just do if you kind of look at it algebraically? Well, what are these two numbers? This is the first column of my matrix. Right? And so this gives us one way to kind of interpret the different columns of our matrix here. These are the images of the different coordinate vectors under the action of your matrix. Right? So if you're ever trying to find like a clever way to assemble your matrix, one way to do it is say, okay, where did the x-axis go? Where did the y-axis go? And make those the different columns. Does that little trick make sense? Because similarly here, we have C11, C12, C21, C22, C1, of course that's equal to C12. So it's just a mnemonic to remember. I mean, it's like pretty obvious. Essentially all I did was multiply C by the identity matrix. But to me, sort of geometrically, this is meaning. Yeah? Right, so let's do an example of that. So let's say that I have a point P, which is in coordinate system 2, yeah, and I want to get P in coordinate system 1. We're going to do a couple examples now, right? And of course, what we kind of convinced ourselves in our last class is that assuming our transformation doesn't involve anything projective, it can be written in a matrix that looks like this. Okay? So, right, and how do we put these things together? We just multiply on the left, right? So I want to go from 3 to 1. I can take a point 3, multiply by 2, 3, put it in coordinate system 2. And then 1, 2, put in coordinate system 1. And now you can see why this notation is kind of nice. I can just read left through. Yes?
Just really for this. What was the P and Q last column?
Right, so this comes from so this is a two-dimensional transformation, right, but in projective coordinates. So that's a great question. So let's say that I have a point, which is the origin. Let's start with that. So, I'm actually going to be lazy and say that my matrix looks like this. P, Q, 1, 0, 0. Yeah? What is the coordinates of the origin in projective coordinates? Emily, what are the coordinates of the origin in projective coordinates? I'm going to pick on you because I asked you the same question last time.
The coordinates of the vector equation.
Yeah, so remember the origin is the point 0, 0. So if I want to convert a point to projective coordinates, what do I do? Just
0, 0, 1.
yes, exactly. Great. 0, 0, 1. Okay, I promise I'll stop picking on you later. Okay, this is what happens when you're like one of two students whose name I remember, but we've been working on this in my office. Okay. Well, so let's take the origin and multiply it by the action of this matrix. And what do I get? I get 0 times some number I don't care about, 0 times some number I don't care about, P. Similarly here, I get Q, and 1. So what does this matrix do? It takes the origin, written in projective coordinates, and translates it to a point PQ. So in general, what this matrix does is that it applies a linear operator to vectors, and it translates at the same time. Yeah. This is just a slick way to do it. Great question. Okay, so let's actually do an example or two of that drawn from my favorite list of affine transformations here. Okay? So in particular, let's say that I want to get the matrix M12 for what we're going to call in today's lecture T, which is going to take a point P comma Q, right? So these are coordinates, and move that to the origin and vice versa. Okay? Well, let's actually apply the trick that we just did. So for one thing, does this matrix rotate or translate? It only translates. Yeah. So what do we know about the upper 2x2 block of this matrix? It's the identity. Cool. Yeah? So we're in pretty good shape. Yeah? Because remember, we always have this kind of structure. So all we're missing are these two values. And in case you can't remember what they are, neither can I. But what do we know? We know that if I take, so let's see, we're going from coordinate system 2 to coordinate system 1. You can see that little arrowhead there? This is where I'm going to constantly get this backward. Okay, so if I take the origin here, what should his new coordinate system be, or his new coordinates be? I hear people whispering. Speak up. PQ, thank you. Yeah? So in other words, if I put the origin in, I should get PQ like that. Does that make sense? So you can kind of guess from here that your last column under, right? Just using the trick we showed in the last before. And other. Yeah. Does this make sense? Cool. Let's do another example. This is my favorite one to get wrong. So let's say that I want to rotate counterclockwise by an angle theta. Okay. So I have a point in coordinate system 2, and I want it in coordinate system 1. Yeah. This is going to be a good review, right? I think, was it Ara was in my office just the other day asking about this? Excellent. So, right. So, let's say I want to take U2. So remember the coordinates in coordinate system 2 are like U2 comma V2. Yeah? So what is going to be the image of 1 comma 0 in our new coordinate system? Well, we can work it out, right? I can turn on the lights and stuff. A little better. Okay, so let's draw it. So here we have here's U2. This picture should look familiar. All right, this distance is 1 because it's a unit vector. Yeah. We have an angle theta. So what is the x coordinate? Yeah, cosine of theta. The y coordinate is sine of theta. There's the theta, in case you're wondering. I'd say everybody in like one of these in there. That's good. Okay, so in other words, this thing should go to in order to complete this matrix, we've also got to know the image of the y direction. This one to me is a little more annoying. Where does he go to? Or she? Let's see. Here's theta now. Yeah, so what is the x coordinate? Somebody other than the two gentlemen in the front row? Literally anybody other than the two gentlemen in the front row? Yeah. Negative sine theta. You see the sine theta is this distance, but we're in the negative direction here. What is the y coordinate? Cosine, yeah. Okay. So what does our matrix look like? Well, we know a few things. So let's do this in projective coordinates. So remember, these are vectors the way I draw them. So what do we know? We know that our matrix times 1, 0, 0, right, because it's a vector, is, I'm going to be lazy and say it's cosine sine 0. I can say matrix, by the way, in code, often people do that. 0, 1, 0 is what? Minus sine cosine 0. And matrix times 0, 0, 1. What is this thing? This is the origin, right? It's a point, because there's a point because you see a 1 and a 0, 0. And does our transformation do anything to the origin? So what should be the right hand side? 0, 0, 1. Exactly. Everybody following so far? Cool. Do I have to have a 1 here? No, because these are vectors. Oh. Yeah, caution. Okay, so it turns out it doesn't really matter in this particular case. But, right, so using our trick, look what we did. We said m times this thing is this vector. So in other words, this vector is the first column of m. This vector is the second column of m. This vector is the third column. Do I kind of like this trick? I think it's easier to reason about it this way instead of writing down all of m as one giant matrix. Obviously, these are completely equivalent. It's just kind of a pedantic way to think about it. And if I'm really lucky, oh, I didn't put it on the slides. Great. So of course this is correct. Great. In fact, let's because it's not on the slides. Let's try to explicitly. So m of theta is cosine say sine theta 0 minus sine theta 0. And that looks about right. Yeah. And this is probably a formula you guys have seen before. Cool. Right, so yeah, that's the basic way that I go about reasoning through how to derive these kinds of matrices. Yes? Cosine. Yeah.
So if you like show the last slide, my question. So like when you're going from O1 to O2, you reason about it the other way.
And you are exactly the reason why I always get confused on this kind of stuff. Yeah, so I think the words from and to here are like a little ambiguous. So the way that I think about this personally in this kind of notation is it takes a point in coordinate system 2 and returns a point in coordinate system 1, and then I draw this entire picture and just reason about this sign. Right? So in this case, we see that these two guys are displaced by a vector PQ. And I say, okay, well, a point, the origin in system 2 is now PQ in system 1, and that's how I think of, that's how I would construct this matrix. This is easy to get backward.
When you multiply the matrix, multiply it by a point.
Yeah, because you remember multiplication takes stuff on the right and outputs stuff on the left. Yeah. Yeah. And anybody that's doing linear algebra with row vectors should be lectured to sternly. You don't do that here. Okay. Except in like in differential geometry, you call a row vector a covector, and it's like an operator that takes that class. I digress. Okay. Right. So yeah. So what do we want to do if we want to rotate and then translate? Well, it's real simple. I rotate and then I translate. Notice that the way that I'm saying it and the way we're reading it are backward. These are all just common bugs in people's code, and I'm excited to see them on your homework despite the number of warnings. Okay, so remember that when I say rotate and then translate, I have to read from right to left because I put vectors over here. Okay, cool. So in today, essentially the difference between today's lecture and our last lecture is that we're just going to do more than one of these. We're going to rotate, translate, rotate, translate, rotate, translate. And the reason for that is that, you know, with your finger, I can write in the coordinates of your hand and your elbow and whatever this thing is, your shoulder, and so on. Yeah? And so that's really as simple as okay. Everybody have something? Cool. Okay, so now let's talk about kinematics, because that's really what's sitting on this stuff. Out of curiosity, how many of you guys have seen the term kinematics somewhere? I imagine a lot of you guys, as computer scientists, have at least seen people throwing it around. If you haven't, we're about to talk about it. No worries. Okay, so we're going to talk about two flavors of kinematics, forward and inverse kinematics. If you're in the know and you're hanging out with a bunch of roboticists and graphics people, you call the second one IK. I've never heard somebody call it FK, though. I would shy away from that. Right, but in any event, the basic thing that we think about in the kinematics world is joints. Right? And so kinematics is all about like robotics kind of equipment where everything is glued together by like a ball joint or a thing that extends, like really simple objects like that. Right? And so essentially a joint is a thing that connects together two rigid objects and allows for relative motion. Notice that this is a formalism that's all about things that are built out of plastic pieces. It doesn't allow for like things that are gooey. Yeah, we'll talk about that later. And there are many different types, right? There's a hinge joint, that would be like the door. There's a ball and socket, like your wrist, I think. Yeah. There's a saddle joint, which I'm not sure what that is. A sliding joint, like the feet of our tripod back there. And essentially they have somewhere between 0 and 6 degrees of freedom in 3D. Right? Can we count? Can we figure out why there's 6 degrees of freedom, by the way? So how many degrees of freedom are there in translation? 3, right? You can translate X, Y, and Z. How many are there in rotation? That's a little bit trickier. Well, there are 3 because the total is 6, but does anybody have any idea why? Yeah. Are you raising your hand or just demonstrating? Yeah?
Rotation around the x-axis is y-axis and z-axis.
Yeah, so that would be one way to think about it, like roll, pitch, and yaw. Yeah. The different one, because my background is in harmonic analysis, is to think about a matrix M, which is, you know, remember that a rotation matrix satisfies this property, right? That M transpose M equals identity, right? So in general, linear thing has how many degrees of freedom? 9. Okay. So it's 9 modulo some number of relationships here. And there's actually 6 because only the upper triangle map. But anyway, any of these things will get you to the same place. Thinking about roll, pitch, and yaw is perfectly fine. Yeah. Right. By the way, by convention, when we talk about a 0 degree of freedom joint, that has another name. It's called glue or a nail. Essentially, it's a thing that just doesn't move. Yeah. But every once in a while, that can be useful too. Okay. Right, so in character animation, of course, joints are extremely critical. And if you go to a conference like Scenic Graph and you see people talking shop about computer graphics, you'll see a lot of people that work with these diagrams, like this funky human guy over here on the left-hand side. Right, so this is some humanoid figure where we've roughly modeled the different joints. And the reason why we spend a lot of time looking at figures like this is because they very clearly illustrate the motion that our animated character is taking. Right? And so a pretty typical thing to do in the graphics pipeline would be to put a lot of effort into animating the motion of these big joints, and then maybe let a physical simulation take care of like your skin flushing on top. Right? And so that's kind of a typical division of labor. It's worth knowing in some areas, especially in video games, you actually have to come up with controllers that control these joints automatically. And there's a huge literature, for example, in reinforcement learning that tries to teach these things how to walk. And it's kind of fun to watch. I encourage you guys to like search around and look at the reinforcement learning for humanoids. And it really is just like humans learning how to stand up. Like I have two little nieces, and it's fun to compare the way they're doing it to like these IK things, and they're remarkably similar. Yes?
I think Google made a fun video about like, it's like neural net for like humanoid learning how to like navigate an obstacle course.
Yeah, there are all kinds of, like you can sit on YouTube and watch these things all the time. There's also animal models too. It's something a little sad to watch because like when you train these things, you kind of hit these humans with a stick and you want to make sure that they can get back up, right? And so that's part of the reinforcement learning is you don't want to just like have them encounter an obstacle and fall. And so the training procedures are like kind of sad to watch, like somebody clicks and then also they're like, you know, tossed over to the side. But you know, of course it's better to do it virtually. If you go to Russ Tedrake's group at MIT, you'll see them actually basically next the same thing, but for an actual heavy robot that's walking around, and that's a little bit sadder to watch. Okay, right. So there are a lot of different state parameters that we can talk about when we talk about joints. There are too many words on this slide, but typically they basically correspond to what we've already talked about, right? There's an offset, which is like translation, and there's an orientation, which is like rotation, right? In certain really bizarre materials, you can also actually have other motions, like shearing. Right? A good example are these, sometimes you see them, I think you see them on the arms of lamps a lot. Let me see if I can draw this. We have a system of joints that looks like that. Have you guys seen this before, where you have these like kind of pair of scissors and you push them together and it extends in that direction? Right, so there's some kind of shear that's happening in this physical thing, even though it's rigid. I think that's pretty uncommon, but it's just something to be aware of. And then the third thing, which for the most part we're going to ignore today, but of course if you're in real graphics, you should think about quite a bit, is that there's typically a limit to how much you can rotate or translate. That's certainly true for human models, and one of the most typical ways that you can really confuse people when you're watching an animated film is to violate that third thing. Okay. For example, have a character whose elbow inverts. Okay. So let's fill in a little bit of detail here. So here's a pretty typical looking diagram. So here's a fisted arm, and so we have three different coordinate systems, right? There's this point here, which is distance 4 away and is rotated about 30 degrees upward from the last guy, and so on, right? So it's 45-degree angle here. But now the 50-degree angle that his elbow experiences is different from the angle all the way from the origin. Okay? And that's where the headache goes into. And so the problem of just figuring out, like, okay, but in the coordinate system of the world, where is your hand? That problem is called forward kinematics. It's like kind of a big name for like a thing that you guys probably already knew how to do, right? So forward kinematics is just like given a big pile of matrices, multiply them together. Yeah? Okay, and so the basic idea here is that I give you a base and a bunch of joint angles and displacements, and the way that you're going to prescribe, for example, a guy walking, right? There's a phrase for this, they call it a walk cycle, right? Which is like one time of your leg coming up and going back down, is to give sort of a spline, for example, in knee angle space, right? And that's going to be the thing that controls your motion. So what are the kind of positive and negative aspects of the forward kinematic? Well, the positive aspect is it's kind of easy to work with, right? At the end of the day, if I want to know where a point is, I just multiply a bunch of matrices together, and that gives me the position. Can anybody think of a negative of working in this particular kind of set of coordinates? Think about it this way. Like, let's say that I tell Larry I'd like him to control his robot to pick up his water bottle here and put it on the floor. And the controls that I give Larry are like the different joints in his arm and how they bend. Is that an easy problem? No, right? Like essentially when you pick up, if you want to even just find the coordinates of the floor in terms of your hand, there's all of these different joints that are involved, right? So what looks like a very simple operation in this forward kinematic model, if you're describing it in terms of the world around you, is actually quite complicated. Yeah? And that's where this stuff starts to break apart. Right? Okay, but in any event, the sort of mathematical formalism here is pretty straightforward, right? Essentially, you're given a long list of joint angles and end effectors, you're given a bunch of essentially parameters of your transformation, right, like the joint angles, and your job is just to output where everything is. In robotics, we call these end effectors, because it's certainly the effectors are the things that can grab onto stuff. They affect motion. I'm guessing that, by the way, I have no idea. Right, and essentially you can think of it as just some function, right? It's a complicated function that's multiplying a bunch of matrices together, but it is just a function that goes from a set of angles to the positions of your hand and your elbows and your shoulders and so on, in one long vector. Does everybody make sense? This is just notation. Yes?
Because you said earlier it's hard to find the coordinates of the graph. It's hard because you have to multiply all these matrices, or it's like it's hard to think about?
It's a good question. So what exactly is hard here? So what's hard is actually directing the motion of picking something up and putting it down. Because if you think about it, like if let's say that it would be kind of like what's a good example? Let's say that I give you one of those goofy devices that you pull a handle and the hand closes, and in addition I just put that in a ball joint, and I say I would like you to pick up something out of the refrigerator and put it on the counter. And the way that you're going to control that is by just controlling the roll, pitch, and yaw of that ball joint. That's essentially what's going on, right? I've given you the coordinates of some object in the fridge in world coordinates, but you're stuck working not just in like some translated coordinate system, but in one that's like rotation coordinates, right? And so there's like sines and cosines and things that you need to invert to figure out even just where to grasp. Yeah, it's a great question. Okay. Right, so the forward kinematic model at this point is pretty straightforward, right? It's just to find the position of a point P, which maybe is written relative to the hand, right? This robot seems to be giving us the thumbs up, maybe. And in order to do that, we just have to chain together all the local transformations. Yep. And how we do that? Well, it's basically what we've already talked about, right? You just chain together a bunch of matrices that are all written in terms of just the local transformations, like rotation, right? So, like for example, M23 here might express the rotation of his wrist, and then M12 expresses the translation of his arm and the rotation of this joint here. Yes?
Kind of just like adding something to what he was asking. So why can't you just compute like the relative position of your hand to the refrigerator or to the object that you'd like to pick up? Like it wouldn't necessarily have to be in world space coordinates because you can always change the rotation matrix or whatever matrix you'd like to apply when it comes to going from coordinate system X to coordinate system Y. I guess I'm still struggling to see like the difficulty.
The difficulty of the actual control problem.
Yeah, or I guess like, because you can always switch, I guess, if you're trying to define the relative position from your hand to the refrigerator, you can always find some coordinate system to map those two things
Sure.
together.
Let me give you a concrete example.
Yeah.
So, let's do this in two dimensions. I'm glad you guys are thinking critically about this. This is great. So let's say that I want to model my arm. And to make my life easier, I'm going to see my arms glued on the wall. Okay, so here is the origin, and over here is some object I want to pick up. Maybe it's okay. Okay, and my arm I'm going to model using two angles, right? So one is the angle of my elbow to the, or whatever this thing is, shoulder to the origin. We'll call that theta. And the other one, so I'm going to extend my shoulder a little bit and look at this angle, which is phi. Which one's phi? That one. And and that describes my arm. And both of these are just unit length. Okay? Here's my question for you. Let's say I want to grasp onto this soda bottle, and he's position x, y. what combination of theta and phi will put this point at position x, 1. That's the formula you need, right?
Okay. Yeah.
And that's real tricky, right?
And so that's what you were saying about like the constraints about forward kinematics, that you can't do it, you can't invert your matrices to go from x, y back to your original coordinates.
Because the matrices have cosines and sines inside them, right? That's right here.
Okay,
Yeah, so that's a great way to think of it, right? And so why is forward kinematics easy? Well, in forward kinematics, I'm saying given theta and phi, just find me the position at this point. That's straightforward, right? That's just trigonometry. The inverse kinematics problem says, given a point, give me the theta and phi and try to make my arm touch them.
Okay, that makes sense.
And in fact, to make matters worse, let's say that my soda can is very close to the origin. Yeah. So here's the thing about this problem. Here are two solutions to this problem that are equally good. Which one do I want? And in 3D, of course, there's a whole cylinder worth of solutions to this problem. And so it's actually an unstable thing to solve. So the forward problem is nice and unambiguous. The inverse problem is extremely nonlinear and maybe non-unique. And in fact, to make matters even a little worse, and then I'll shut up. If I take my can and I put it out of reach of the robot, so like here's the circle he can reach in. Am I likely to be able to detect this scenario easily if I'm given a bunch of crazy parameters, phi inside? No, this is some nonlinear thing. It could be I'm just not seeing the solution, right? And so, yeah, it's a very tricky problem. And one that people continue to study. Okay. Right, so in any event, the forward problem I think is something that you guys are all capable of, and I hope you are because you're all going to do your homework. We have this little like skateboard dude with a backward hat, and your job is to like put his arm in the right place. And so the way that you're going to do that is chain together rotation, translation, and so on. And then once you have a skeleton in the right place, then you're going to put skin on it, which is the topic of our next session. Okay. So again, the pros and cons here. The pros are that this hierarchy is very efficient and simple to work with. Essentially, you just need to know the relative motion between every joint and the thing right underneath it. And so especially when you're modeling like motion in open space, you're doing yoga, there's nothing to run into. You're not somebody like your instructor who just finds things to run into. Then these things do quite well. But when you interact with your environment, for example, you want to pick up that soda can, then things get tricky. Okay. So to add a little bit more detail to that, the reverse problem of trying to find these angles, given some end effector position that you want, that thing is called inverse kinematics. Again, IK, if you're in the know. This is sort of saying, given a desired location or maybe even an orientation of your end effector, figure out all the joint angles to put things there. Yep. And this is tricky because remember we defined this function f, which goes from all the thetas to the positions. Now I'm saying I really like that inverse, but I don't have it. So lots of different ways to understand this. Okay. So in the same notation we developed before, essentially now, rather than being given the thetas, we're given the e's, and our job is to find the thetas, given this implicit relationship, right? That theta equals g of e. And so at the end of the day, what is this? Well, it's just some system of equations that I have to solve. Just some system of equations. That happens to be NP hard to solve, but it is just simple as theta equals g of e. And so finding a solution here is quite hard. There can be cases where there's an infinite number of solutions. That's called under constraint, right? So for example, here the arm reaching the soda can, there's a lot of different solutions that are all okay. There are other cases where there's exactly one solution. For example, when the arm is completely extended, and so on, there are none. And it's very difficult in general to detect these cases by just kind of looking at the configuration of the one. Maybe in this case it's not so hard, but I can imagine adding lots of joints and making this pretty complicated. And so typically you can't solve this analytically. Hopefully you guys know what this phrase means, solving analytically. It means basically just writing a formula for the solution. Right? So instead, you're just like solving some crazy system of equations. But in a sense, we're okay with that in the graphics world. And indeed, when we talk about class simulation, we mean exactly the same scenario. In fact, you'll all have to implement some small version of that. And so the typical thing we have to do is use some numerical, like number crunching strategy for solving this in practice. And it's real complicated, in case I haven't driven it home. Like for instance, here's a pretty typical looking problem, right? You're given all of these different, roll, pitch, yaw, and then maybe translation hiding in there, and you've got to find all of these things at the same time. By the way, if you still don't trust me that this is a hard problem, take any of these guys and add 2 pi to them, and does my solution change? No. So either like my solution is just never unique for this problem, just a giant head. Okay. So in order to do this, we need to dredge up some more calculus that you guys probably don't remember. That's okay. And this is an object called the Jacobian of a function. Yeah? So remember that our function f here takes in many inputs and outputs many outputs, right? Because it takes in all of these different angles and it outputs all of the different end effector positions. Right? So if you look at all of the different partial derivatives you could take of basically every output with respect to every input, that's this matrix called the Jacobian. So one way to think about it is it kind of gives you the instantaneous change, right? Like it looks like d effector, d angle, right? And that's essentially what it's giving you. Does that make sense? So, right, so to first order, what does my problem look like? This is going to be just like your instructor can't ever get indices correct. I'm also really bad at Jacobian versus its transpose. Yeah, but roughly, for example, let's say that I want to know f of theta plus for small changes of theta. What could I do? Well, this is roughly equal to what the f of theta. This would be the world's simplest approximation. This is just saying it's close to pi. Right? And then if we want a first order term, what would I do? I would take the Jacobian of theta multiplied by d theta plus, now we're going to be sloppy. Right, so this is some approximation in small. Right? I think we've all seen this in Taylor series. Is there a transpose here? I don't think there is. Okay. Cool. Excellent. So right, so this is some local approximation. So what do you think we do? So let's say that I want to find I'm trying to solve a system that looks like this. F of theta equals E, right? And I have some approximation theta I, right? So and this is kind of like E, but I'd like it to be even closer to E, right? So what I really like is that E is F of theta I plus delta theta, right? So in other words, this is F theta I plus J of theta I plus, and then we're just going to remove the higher order term just as an approximation. Yeah. So at the end of the day, if we solve for delta theta, okay, what are we going to have to do? We're going to have to invert the matrix J, yeah, and then add that to theta I, right? Because it's going to give us a better approximation of our root. But is it the actual root of our problem if it's nonlinear? No, right? Because I cut out my higher order term. So what do you think I do? Just iterate, right? And does anybody know what this algorithm is called? Let's start guessing famous scientists' names. Newton's method. Yes, exactly. Yeah. Exactly. So anyway, this is a definition of the Jacobian, and if you want to use Newton's method to do IK, thank you very much. Then essentially you can see what ends up happening is we solve a linear system that looks like J times delta theta equals delta G. Right? This is like sort of G minus the G that you had in the last iterate, right? Which makes sense. And then you add that delta theta to your current estimate, and then you iterate to compensate for the fact that your problem is okay. I'm not going to ask you guys to actually code this on your own. This is just a thing that you should know at a high level, because in reality, this algorithm really works, and there's all kinds of crazy things you can do to make it stable. But roughly, if you read through an IK research paper, probably hiding in there somewhere is an algorithm that looks like this, plus a bunch of accoutrement for like when you divide by 0 and things explode. Because approximations don't ever fully perfect. So this is the one you always see in textbooks. Right. By the way, I think on your homework, one of the things you can do is actually implement this for extra credit. If you're like looking for excruciating pain, I highly recommend you give this a shot. Right. So what are the pros and cons here? Well, the pros are that like there are a lot of kind of action-oriented things that you can do in IK that would be very difficult to do in forward kinematics, right? Like pick this thing up, put it there, right? That's the kind of thing that I'd like to describe in terms of world coordinates, but the reality is that my effectors are not in world coordinates. This is just a problem that's hard to solve, right? I have to use some crazy Newton's method here. I've got to invert matrices. I haven't actually shown you that Newton's method has to converge. There's a lot of things that could go wrong, right? And that's actually really why when you see in video games like characters snapping around a lot, that typically what this is what's going on behind the scenes. That said, inverse kinematics, unsurprisingly, is an area that people in robotics, computer graphics, and a lot of other disciplines really care about. And so you see a lot of really interesting work. So for instance, here's some work from MIT from about a decade ago, where they talk about mesh-based IK. So like, I want to have a 3D model posed in different ways where maybe I grab a few vertices and place them, or like an elastic deformation everywhere else. And so in mesh-based IK, maybe as input, rather than given a skeleton, you're given a couple example poses of a 3D shape. And now your job is, like, I drag this vertex somewhere that's not one of the example poses. Can I use these two guys to kind of fill in a plausible motion in between them? And so this is a pretty important technique in processing. And remarkably impressive. Like, I mean, if you guys think about what it would take to solve a problem like this, it's not so obvious. Okay. This is, by the way, a good course project material. This stuff isn't that hard. Right. So now, for our final topic for today, let's talk about hierarchical modeling, which is sort of what we pulls out their watches, pulls out their bags. It's going to be a long final topic. Okay, let's talk about hierarchical modeling just a bit here, and the Scenic Graph that appears in graphics system. Okay, so typically when we talk about one of these 3D skeleton models, we describe it in kind of a tree structure, and I think this makes some sense, right? So I put some root node maybe in its pelvis, and then I have this whole set of transformations that maybe raise the pelvis in terms of the root, the hips in terms of the pelvis, the knee in terms of the hip, the ankle in terms of the knee, and so on, right? And the reason to do that is that basically by using what we did at the very beginning of today's lecture, like just simple trigonometry, these individual edges in this tree, hopefully you guys are convinced are not so hard to work out. They're like a little bit of a headache, but not a huge one, right? Whereas the transformation that goes directly from your pelvis to your toe is probably not a thing that's easy to reason about. Yeah? And so that's the basic setup. And it really, it looks like a data structure, right? We're all computer scientists, and this is like screaming out for us to code in exactly the fashion that we see on the screen. Yeah? Incidentally, is there like a convention for choosing the root node? Not really. It kind of depends what studio you work at, right? There's no, God didn't tell you that your origin is like your okay. Right. So how do we actually render this model given a tree like this? Well, it's typically done using the depth first recursion algorithm. Many of us have seen depth first search somewhere. Excellent. So here's the basic idea. I start at the root tree. I go down one of these edges, and every time I go down an edge, what do I have to do? I have to kind of stick a matrix onto the end of all of my coordinates, right? And now I'm at a vertex, which says I have a 3D model of your torso. What do? I take all of the vertices of your torso, and I multiply it by the current matrix, and then I render, right? And that matrix implicitly translated to screen coordinates. Do I care about like what those entries mean? No, not really, as long as it's the thing that takes me to screen coordinates. You can see that this is a nice encapsulation, right? And now, when I move down the edge, what do? I take the last matrix and I pre-multiply it by the torso to neck matrix. Actually, I got it backwards. I post-multiply. Yeah. And now, when I render the neck, as long as I remember to pre-multiply by that matrix, which is really the composition of everything I've seen so far. So every time I see a vertex, like I just without thinking about it, I hit it with that matrix. Then implicitly, I'm doing stuff in world coordinates, even if it looks like I'm doing local. Yeah, really nice basic idea. Yeah, and it really is ripe for a recursive implementation. Right, and so what we have to think about is how to handle these transformations. Right? Each transformation is written in terms of the coordinate system of his parent. Okay, so that really leads to this question of how to traverse the hierarchical tree. And basically the algorithm is pretty simple, right? You draw the current node, and then you recurse to each of your children, right? You kind of pre-multiply your current matrix by the matrix that sits on the edge, and then you just draw everything in that node and recurse all of their children. Right, and once you've visited each of your children, before you go back up the tree, you've got to undo the fact that you multiplied your current transformation. Yeah? Incidentally, the thing I want you to think about for 5 minutes while we continue talking about hierarchical trees is how to undo. Yeah? Okay, so as an example here is a thing for rendering a scene with, I guess, a table with some fruit on it, and a laptop, and chairs, and so on. Right? So what does my algorithm do? Well, it starts at the root. Right? So my current matrix, just by convention, is the identity. And the idea is that anytime that I render a point, I'm going to multiply it by s. That's just what we're going to agree on. Okay? And in fact, in OpenGL, at least until the latest version, you would actually give OpenGL s so that like, when you're rendering something, it's actually transparent to you that you're rendering it in some other coordinate system. OpenGL just knows that you should multiply stuff. People didn't like that, so it's actually gone now. Right. So now, I want to translate before I draw the table. So what do? I stick onto S, my translation matrix. And now, when I render every vertex of the table, I first multiply it by S, which implicitly translates it back before I draw it. Okay? So now, if I want to render the legs of the table, there's some other translation for the legs. I go down that. And when I render the legs, they first get multiplied by T2, and then by T1 to go from leg to table to world. Right? And the tricky part is that now I got to go back up the tree. I got to get rid of T2 and T1. And then maybe, oh, oops, I'm pressing the wrong arrow. And now when I go to the rotation here, notice that I put it on the right-hand side. Do you guys see why? Right, because when I render the basket here, I want to first rotate to go up there, and then translate to go up here. Right? So when you keep track of your pile of matrix multiplies, you kind of put them on the right-hand side. And so, right, so now when I traverse, I go back up this thing, I go to the identity, and maybe I go the other direction. Does this algorithm make sense to you guys? Cool. And so in reality, graphic systems have these giant trees of all this stuff that are linked together, and maybe really one of these nodes is some other CAD file which has its own tree inside of it. And it can get pretty complicated pretty fast. Right, and so if you ever want to go to find the matrix that takes you all the way from this thing to world coordinates, you traverse this tree and then just look at the product. And when we talk about skinning, that's going to be really important. Because in skinning, essentially, you're going to have a 3D model, right, like of a human and some rest posts. And there's going to be a skeleton embedded inside of it. And I'm going to move the skeleton, and I'm going to want the skin to go with it. So how am I going to do that? I'm going to take the 3D model, I'm going to write it in the local coordinates of the bone. Then I'm going to rotate the bone, and then I'm going to undo all the stuff that I just did. So we're going to have to reason quite a bit about moving up and down this tree. Yeah? Again, this is all like stuff that's really easy to get wrong. That's the impression that you should get. And I can talk about it all I want in class, and you're going to try it at home, and then you're going to learn about it. That's how this kind of thing goes. Yeah?
This would be like too in-depth, but like I was wondering, like, so let's say you're at the root, right, and you want to find the transformation of like your left index. How do you know where in the tree that is?
How do you know where in the tree that? Yeah, that's a good question. So you're saying I want to know where the left index finger is, but well, typically if you're asking where the left index finger is, you probably know where it is in the tree. At least you know in the data structure where that object is. And so typically the way that we store trees computationally is that maybe every vertex keeps track of a pointer to its thing above it. What was that? Parent. Thank you. So this would be just a linear thing. Yes.
Yeah. So you talked about how you might render given this tree, but let's say you want to update parameters, like you want to do your physics computations. Do you do these physics collision computations in the local frame, or do you put everything in the world frame and then?
Yeah. So to continue in our example of my colleague up here, if I have this guy and he's swinging a tennis racket, and then the ball hits the tennis racket, this is going to be a giant headache, right? Because the ball is in world coordinates, the tennis racket is in like hand coordinates, and you're right, physics is really, really hard in that case. So you have two options for this. In movie studios, often what happens is one person does the animation, and they hand it off, and the physical simulation people can translate everything to world coordinates before they simulate. Or in a video game, you can't afford to do that. So maybe you actually write Newton's laws in the end effector coordinate system. Like rather than f equals ma, you like say, well, what does that imply about the angles, and work things out that way. So those have advantages and disadvantages. If you want to see something really cool, search for discrete geometric mechanics, which does all of physics in that weird coordinate system. And there's some interesting conservation laws that come up. But I digress. Okay. So in any event, right. So we're traversing this tree and we're keeping track of our state as we do so. But there's one detail that I kind of skipped, which is if you undo a vertex, and I want to go back up to his parent. What should I do? Well, one thing I could do would be to look at that matrix which is sitting on the edge of the tree, and to undo it, I can post-multiply by his inverse. Yeah. Why could that be like not such a great idea? Yeah.
You have a big tree, you end up with a really long complication.
Well, it's a factor of 2, right? You already multiplied to go down, so I want to go back up. A constant factor. We're kind of doing that. Yeah.
The precision issues, or
precision issues.
Yeah, you might not end up with identity matrix.
Yeah. So in general, let's say I take I multiply 2 numbers together, x times 1 divided by x, and I'm a computer. What is the output of this number for this calculation? I mean, let me give you an answer. Is it 1? No, it's 1-ish. You see that? Because essentially, this number here, right, 1 over x might be something with an infinite number of decimal points. Right? So if I do this calculation, I truncate it a little bit. So this is no longer 1 over x, it's 1 over x-ish. Yeah? And here's the thing about this graphic system. How big are these trees? The distance from the root of the tree all the way to the bottom can be like miles. Right? There can be a ton of different transformations that get multiplied together. Right? And think about what's going on. You're going down and up, down and up, down and up, down and up, down and up. And every time you do that, if you multiply by the inverse of a matrix, you incur just the tiniest bit of error. Now, roughly how many triangles are on a typical industry level triangle mesh? I guess just order of magnitude. A few 100,000. That's a lot of triangles. Hella triangles. Yeah? And so there are like a lot of opportunities to get this thing wrong. Yeah? And so rather than doing that, we're going to propose a different. Yeah, so anyway, here's a reason why you shouldn't invert a matrix. For one thing, t times t inverse does not equal the identity in our world. It equals the identity kind of, sort of. Yeah? And this is particularly true in graphics because often we'll actually use fewer decimal points than in scientific computing, for example. Because at the end of the day, you're rounding to like a pixel, which is like a pretty big unit. So like doing math with like a gajillion decimal points is probably overkill. So to make a graphic system fast, we'll often use these kind of short or even fixed precision kind of numbers. But those are particularly inaccurate. And to make matters worse, I didn't tell you that t couldn't be singular, like non-invertible. Like for instance, maybe I have a 3D object and I just squash it onto the plane, in which case I couldn't invert. Yeah. Right. So any ideas what we do instead?
You can just store the matrix at that point.
Yeah, you can keep a stack, right? And so every time I go down, I'm going to keep around the old matrix, but put the new matrix on the top of the stack. Yeah? And now when I go up the tree, I just pop the stack and get rid of it. Yeah? And relative to the amount of memory that I need to just store that tree anyway, this is like nothing, right? And so that's the typical solution. Is to keep your matrices on a stack. When you enter the node, you push. When you leave the node, you pop. And this is built into most computer graphics libraries, and is what you'll implement on your next homework. However, one thing that's worth noting is that it is not built into modern OpenGL. You guys have already heard me kind of wringing my hands about this a little bit. Essentially, the most modern graphics libraries have removed all of these software features. It's actually kind of an interesting development historically. What they've decided is that this is your problem. This is some software thing. Right? The job of the graphics library is just to let you talk to the GPU. Right? And anything else that we do is us passing judgment on what you want to do with the GPU. And we don't want to do that anymore. Right? And the reason for that, it actually does make a lot of sense. Right? Like for instance, many of you have probably heard of TensorFlow and all of these things for deep learning, which also make use of your graphics card. But if you had to write them in terms of like matrix multiplies, you wouldn't be too happy, right? And so the reality is that your graphics card is just a really good SIMD processor. This is something we'll come back to later in this course. Anybody know what SIMD stands for? Single instruction, multiple data. It's kind of like, you know, the comedy sketch where Lucille Ball is working at the factory and there's like this long conveyor belt of pills, I think, that she has to put in little containers and they just go across. Right, your tells just pick it up, pick it up, pick it up. That's what your GPU is really good at, right? Like it's just good at sitting there and doing the same calculation on a bunch of different numbers. And what we realized in the last 10, 20 years is that there are a lot of computational tasks, for example, in machine learning, that also fit into that framework, but aren't rendering, right? And so the modern graphics libraries say, if you want to render, that's great. If you want to do deep learning, that's cool too, right? And so a lot of these features that were kind of graphics specific were actually stripped out and then left to higher level graphics libraries to take care of. And that's sort of okay also because processors are getting really fast. So if there's a little overhead incurred when you do that, we don't mind as much as we did in 1995. And I was okay. Right. So the key vocabulary word here is a scene graph. This is this thing that we've drawn quite a bit already. And essentially, scene graph is just this nice table, or I guess tree representation of what's going on in your scene. And so the scene graph is sort of a nice logical organization where you can kind of read off what's nested inside of one. And of course, there are many different node types here. You can have a shape, maybe a transformation, maybe a color, where you say everything underneath this node is yellow or whatever. And all of these kind of fit nicely into this basic data structure. And so this is one of the reasons why you often see graphics libraries in C++, because this is sort of the earliest programming language that really embraced this kind of idea of these objects that fit together in structure. Okay. There's one more vocabulary word we need today, which is directed acyclic graph, DAG. Yeah? A tree is an example of a DAG. Right? So the idea of a directed graph, by the way, is a graph where all the edges are actually arrows, right? There's a head and a tail, or a parent and a child. Thank you. Right. But a directed acyclic graph has the property that, well, it's not just a tree. Like everything doesn't necessarily have a unique parent. So, for instance, one example of a DAG, would be this graph. So here's a root node. Here are two children. So far, it's a tree. But if I have these two guys point into one, right? This is directed. Each edge has an arrow on it. It is acyclic. Like there's no loop that I can make because the edges are directed. And it's graph. So why are DAGs useful? So let's say that I'm rendering the great outdoors here, and I've got a bunch of different pine trees. Yeah. I probably don't want to model every single pine tree just over and over and over again and store each one in its own file. Right? Like it could be I just want to take one pine tree and stamp it a bunch of times, maybe with a slightly different parameter. But in this this sort of setup, that wouldn't be possible, right? Because I would need a different tree node after every translation. Whereas reality is you can have a bunch of different translations applied to the same tree, and that's fine. Right? And so that's why the real formalism in the scene graph is a DAG in a tree. Right? So here, I want to draw a big bush composed of lots of little bushes, right? So I have a big collection of different transformations that all apply to the same object. And if you think back to our kind of recursive rendering algorithm, that works, right? I go here, I transform, I render, I go up, I undo that transform, I go here, transform a different way, render again, and so on. Yeah? Are you with me so far? Yes?
So when you write down group, is group itself a DAG, or is it a mesh? Like what is an object?
Yeah, the word group here. Yeah, no, it's what are the axioms? You have an addition, additive inverse. Never mind. No, a group is just a collection of things. So one of these nodes could actually be its own DAG, right? This is just an abstraction. So it's just a node. I wouldn't get on that term. Any other questions? Okay. If you look at the GPU rendering pipeline, this is actually the old. Oh no, it's not. This is the new original pipeline. What does it typically look like? You kind of have the input, geometry goes into your memory. There's vertex processing, primitive processing, rasterization, fragments, and so on. So typically, where these matrices matter is kind of up here, right? So encapsulated somewhere in your probably vertex processing is this matrix which takes into both coordinates. And indeed, this is what's used to render model. So for example, here's that scene that I talked about before. Put bounding box around different objects, things on the inside, and so on. And when you model, that looks like that. I'm kind of zipping through this because I think we've already said it a few times. Okay, so in this class, on your homework, you'll have something that looks like this matrix stack class. This might have changed a tiny bit in the latest version of the assignment, so we'll update this slide so this is a little bit more, which we should double check. Has that gone out? Yes, great. Next assignment's out. So we'll double check these two slides. But roughly, you're going to work with a very simple stack thing, which includes some translation and rotation as well as push and pop. Yeah, so just real basic stuff. And so when you encounter a transform node, essentially what you're going to do is make the new transform that you want, and then just push it onto the tree and pop it when you're done. There's one detail which is going to matter, which is that there's some function that sets the uniforms. This is a new vocabulary word for us, uniform. And the uniform is like a constant that sits in your graphics memory, and it's just a thing that you're going to need a lot. So in this case, the uniform would be the matrix that takes you to world coordinates. Right, so you're going to have this stack, which is keeping track of your current transformation, and maybe that happens in your CPU, because it's just like 3 by 3 matrix math, it's not that much. And then once you've done that math, now you're just going to send it off to the GPU. So one thing that you just kind of have to remember is once you push pop stuff from the stack, you need to update the uniform on the graphics card, which is telling it like, now there's some new matrix that needs to multiply stuff by. This will make a little more sense when you look at your assignment. So you should just dig through and look at this function and make sure you see what it's doing. Yes?
The reason why it doesn't set the uniform to something else after it pops up those things, or just not?
Meaning that like there's a reason why when I pop it just doesn't do this by default?
Aren't like in this particular program, it pops a bunch of things from
Oh, yeah, because if you're not rendering anything, there's no reason to
Okay, so
yeah, you could have, it wouldn't be a big deal. Yeah. To interpret your question the other way, like why doesn't that just happen automatically? That's because all of this stuff with the stack of transformations typically happens on your CPU, like the central processing unit for your computer, because really it's not that many calculations, there's just like 9 numbers involved, whereas like your meshes involve like thousands of numbers. So when you push and pop, it's no big deal. And there's like a little bit of logic and so on that doesn't fit well into SIMD math. And so then, typically you kind of isolate pop from setting the uniform so that you can do things like this and not every single time have to send electrons back and forth to process. Yeah. Okay, so real quick, we're going to spend our last 8 minutes doing the appendix that I promised that has nothing to do with what we've covered so far, which is just so you're equipped to do your next assignment here. And that's how do you cope with normal street surfaces. So before we move on, any questions about scene graphs, hierarchical modeling, trees, stacks, queues? Probably don't want a queue in this class. Yes?
I have a question regarding the offset when you're using the joints.
Uh-huh.
So how do you compute the values with the offset?
How do you value the
I think
offset?
you mentioned like, I mean, because you think, so you mentioned like the orientation, like each joint had its own orientation, but then there was some offset value, like because I wasn't able to see.
Yeah, so personally, I mean, this is a little bit of convention, right? I think typically what you do is you agree with your other engineers, do I translate and then rotate, or do I rotate and then translate, and then you just stick with them. Right? And so these are just 2 different constants, right? There's one which is your bending angle, and another which is your region motion. Any other questions? Cool. Okay. So really quick, one last thing that we need to patch up that actually was on your previous assignment, but we just gave you a formula, and we should justify it now, is dealing with surface normals. This is what we're going to need for rendering, and we're just going to mention it now because when you do skinning, you're going to do all kinds of crazy transformations that get applied to the skin, and if you don't do your normals the right way, like the shading is going to look real weird. Okay, so in case you guys haven't heard this term before, normal to a surface is a vector that points perpendicularly to the surface. Right, so for instance, you can see they point outward on a circle. Well, they point outward on anything. That's the definition. Yeah. And the reason why we care about normals is because they're used for shading, right? So for instance, if I render without normals, the best I can do is one giant red block saying there's a sphere here. With normals, I can get this nice diffuse looking object. And as a quick preview to future lectures, this is an example of something called inversion shading. So this is saying that the color that I get at a pixel is kind of roughly proportional with the dot product between the vector to the light There he is, and the vector and my surface normal. And I think we all kind of know that intuitively, right? If I take like a sheet of paper and I hold it right up to the light, it looks bright, and as I rotate it away, it's getting less photons. Right? And that's roughly what's being encoded. Okay? This is called the inversion shading model. I think you guys could have all kind of guessed it if you didn't have time. By the way, this only works if these are unit vectors, which is another common bug. Yeah. If you're ever unsure in your shading, just in case. Okay. Right. So a quick question here is, let's say that I apply an affine transformation to a 3D shape, and I want to know what should I do to its normals. So I have its normals in its object space, but I'd like its normals in world space. Because that's the basic thing we're going to have to do. Because remember, think about it this way. Like, let's say I'm rendering an elongated sphere, but I'm doing it in the pipeline that I just described to you guys. Right? So I've traversed this tree, this hierarchy, and I've gone all the way to the bottom of the tree, and I'm rendering the ellipse. Does it actually probably look like an ellipse while I'm rendering it to my code? This is where things get a little abstract and weird. In my code, it thinks it's rendering a circle. Do you see that? It just happens before it renders that circle to multiply it by a matrix, which is stretching stuff out. Right? And so when you give the normals to your code, you're giving them in object coordinates. But when you render, you would like the normals to be in world coordinates, and some pretty crazy things can happen. Yeah? This is a subtlety that's kind of tricky. And indeed, transforming normals is actually a thing that's easy to get wrong. So in particular, one of the things you might think is like, okay, well if I take a vertex here and I multiply it by a matrix to go here, then maybe I take the normal and I just multiply it by the same matrix. Is that true? No, otherwise obviously I wouldn't be asking that question. Right, and in fact you can kind of see that in this picture here. So here I took this guy and I multiplied it by shear. And take a look at this object. So I think actually our brains, it's really funny. I noticed when I taught this class in the past, when I ask people, are these the normals, they say yes. Right, and it's because it kind of like it has something to do with this shape. But no, these are not the normals for this. So the normal is straight up. Do you see that? Because this is flat. Okay? But this is what you get when you multiply the vectors by the thing that I just used to shear this object. Yeah, so something a little fishy happened, right? I can't just use the same matrix twice. Okay. Cool. And of course, there are many different types of transformation we have to deal with in this class. So a very typical mistake is, you know, if I do the normals incorrectly, you get something on the top, which kind of looks right, it feels right, because I squashed something up, so I feel like I should squash out the normals too. But in reality, they're still unit-like and perpendicular. This is a common mistake. And indeed, on your assignment, if you get it wrong, here's the inversion shading with the incorrect transformation like this, and you can see you get this giant brightly colored lobe. That makes sense because we kind of stretched out the normals way more than we should have. Whereas here, now you can kind of see that this is an ellipsoidal object. Yeah? Okay, so how do we do it correctly in 3 minutes or less? So there are a lot of different ways to reason about this. The way that I kind of like to do it is to think not about the normal direction, but about the tangent direction to my surface, like the thing that just barely touches it. Because things that barely touch my surface do transform into the surface. Does that make sense? So this is a pretty sneaky thing to do. So in general, we're going to have some matrix M, which takes a point in object coordinates and it outputs things in world coordinates. That's the O and the W here. Yeah? And our question is, what happens to the normal? So we're going to use, once again, basically a proof technique that we've already seen a few times in the last few lectures. And once, for those who were in my office hours yesterday, you saw me get it wrong. So let's see if I can fix that. So what do we know about the normal? We know, in fact, there's, I used somebody else's slides and there's a slight mistake. So that's kind of pleasant. Yeah, okay. So we're just going to relabel his object. So here's my object, and let's say that he has a tangent vector v. Well, say he's a tangent vector in object space. Okay? And he has a normal vector, and in object space, these two things are perpendicular. And now I have a matrix M, which takes me from object space to world space. And think about this. So let's say that I took two very close by points, like x and x prime. right? And I translated them to world space, right? Well, what would happen? X would get mapped to m times x prime, mapped to m times x prime, right? So if I subtract these two things, yeah. So what's going to happen if x prime kind of approaches x? Well, I'm going to get somehow like a vector that points in that tangent direction. And what does this argument show me? It shows me that tangent vector does transform in M. Does that argument make sense? It's kind of intuitive. Okay. So let's look at our picture here. So what is the one thing that we know about the relationship between N and V? They're perpendicular, right? Like that. Okay. So, N object space, dot product V object space equals 0. By the way, do you guys see that this is dot product? If you think of this as a column vector, when I transpose it as a row vector, when I do row vector times column vector, it's like dot product. Okay. So, and in addition, I have V in world space coordinates is equal to M times V in object space. Okay, that's what we know so far. Yeah. And what do we want? Well, we want a normal in world space still needs to be perpendicular to V, but in world space equals 0. Yeah? These are all the things that we know are true. Does this make sense? Now we're going to kind of fill in some space in between to see how to get from here to here. Okay. So in particular, I'm going to erase this line. We're going to come back to it in a moment. Well, what do we know? We know that M times V in object space is V in world space. So I kind of want to put an M there, but I can't. Yeah? But what I can do is say, okay, and in object space transpose, M inverse times M V in object space is equal to 0. I haven't done anything. Just stuck. This is like fancy language for identity. Yeah? Now, why do I do this? Well, let's grip it this way. Yeah? Well, what is M times V object space? V world space. Yeah, excellent. And remember that the transpose of a product is the product of transposes flipped in the reverse order. Yeah. So this is M minus transpose normal object space transpose. Right? Because if I distribute that transpose, they flip order and transpose locally. I think it's easier to read it this way. So here's the thing. What did I just do? What is this object? This is some vector. Do you see that? Okay. So this is some vector whose product with V gives me 0. So what is this thing? Everybody, 1, 2, 3. Yeah, you're all wrong. It's not the normal. Because what property am I missing? It has to be unit length. So this thing is parallel to the normal of my surface. Yeah, but you're close. Okay, so in other words, if I want the normal, in fact, both slides kind of a little wrong, so I'll fix that. But in any event, if I want to get the surface normal, if I multiply the surface by M, then I have to transform the normals by M inverse transpose. Yeah? And so this is one of these things that's easy to get backward. And of course, M, however, if M isn't orthogonal, then this thing could change the length of N, so that I have to normalize it again. Yes? Oh, that's, yeah, the normal could also flip in or out. You have to, like, if M is orientation reversing, then you might get in a little bit of trouble. This is the kind of thing that people just guess and tell them. I'm not gonna lie. Yeah. Right. There's one more thing I wanted to say and I forgot. Oh, right. Yeah, so let's say that M is a rotation. Yeah. So let's explain away why you guys probably got this wrong in your homework and why it probably didn't matter. What is the inverse of a rotation matrix? Rotation by the opposite angle. This is true, but as a matrix, what is this inverse? So remember, rotation matrices are orthogonal. They preserve lengths of vectors. What's the inverse of orthogonal matrix? Transpose, right? In fact, that's the definition of an orthogonal matrix. Its inverse is equal to its transpose. Yeah? So what's the transpose inverse for an orthogonal matrix? Just the same thing again, right? So I think in your homework you did a lot of ridge motions, and so you might have accidentally got the transformation wrong, and it just didn't matter. In your next homework, I guarantee that won't be true. Okay? Yeah, so anyway, just FYI, so if you transform vertices by M, you have to transform normals by M, inverse transpose. In this case, you really do have to compute the inverse, but the inverse of a 3x3 matrix is just a formula you can look up, or actually I think it's provided in your code because we're okay. So anyway, with that, we'll call it a day, and I will see you guys next week. Don't forget about your data quiz and take a look at your notes.